welcome to the Joy of Painting. Now today, we got something very special lined up for you. We've made a few episodes in a series and we're going to call it the X-ray Interactions with Matter. Now, each of these episodes we're going to talk about an interaction, and there's 5 we got to tackle. Now, starting off, we're going to do coherent scatter. This is where your incident X-ray beam interacts with the atom and changes direction. There's no loss of energy there. The next one we got is Compton scatter. Now, that's when the incident X-ray beam ionizes the atom and then changes direction with a loss of energy. Now, after that, we've got photoelectric effect. In photoelectric effect, your incident X-ray is completely absorbed by that inner shell electron, and then that electron is in there ejected, and then we call that a photoelectron. After that, we'll go ahead and talk about pair production. You have your incident X-ray beam interacting with your nuclear field, and you got a pair of electrons coming off of that. And last but not least, we've got photodisintegration, where your incident X-ray beam interacts with that nucleus, completely disappears, and then a nuclear fragment is in there ejected. Now I know this sounds like a lot, but we're gonna break it down real slow, talk about each one, and out of these interactions, the 2 most important we gotta worry about are your Compton scatter and your photoelectric effect. And these will affect your X-ray image, or painting that we like to call them around here. So why don't you sit back and relax, or if you like, grab a brush and paint along with us. We're gonna have a nice time. I'm just glad y'all could join us. So let's get started with our first interaction.
Welcome to coherent scatter, also known as classical and or Thomson. As you can see, I've already painted my atom. So first we'll start off with the incident X-ray. I shall paint that. Okay, the incident X-ray goes into the atom, interacts with it, and as a result, it excites the atom. So with that excitation, you have a scatter X-ray. Yep. So this is scattered. My scattered X-ray. Okay. So with my incident X-ray and my scattered X-ray, they have the same wavelength. There's that one. There's that one. So since they have the same wavelength, that makes them having the same energy. But remember that my incident X-ray changes directions from my scattered X-ray. So with coherent or classical or Thomson, we have no ionizing radiation. Keep that in mind. Also, with coherent scatter, it occurs with energies below 10 keV. But it does have a little contribution for energies of 70 because it creates noise, and noise reduces contrast. So thank you for joining me in coherent scatter. Join with us next time as we paint Compton.
Hello, and welcome back. Today we're going over Compton scatter. As you can see, I have drawn out an atom that a Compton scatter interaction is happening. So what is Compton scatter? Compton scatter are X-rays that can happen throughout the diagnostic range. So what happens is an incoming incident X-ray interacts with an outer shell electron. The incident X-ray knocks out the outer shell electron, now known as a Compton electron. Now the incident X-ray changes direction and becomes a scattered X-ray. This is my favorite part. Just beating the devil out of this brush. Let me get some more paint. So, The energy of the Compton scattered X-ray is equal to the difference between the energy of the incident X-ray and the energy of the ejected electron. The ejected electron is equal to the binding energy plus the kinetic energy of the incident X-ray. The energy of the ejected electron is equal to the binding energy plus the kinetic energy while leaving the atom. So during Compton scatter, most of the energy is divided between the Compton electron and the scattered X-ray. Usually, the scattered X-ray retains most of the energy. Scattered X-rays can be deflected in any direction, including 180 degrees from the incident X-ray. At a deflection of 0 degrees, no energy is transferred. As the angle increases to 180 degrees, so this angle increases, more energy is transferred to the Compton electron. Even at 180 degrees deflection, scattered X-ray retains at least 2/3 of the original energy. If scatter is directed back to the incident X-ray, this is called backscatter. Scatter provides no useful information to the radiographic image. This results in reduced image contrast. Now that you know about the Compton scatter interaction, please continue to join us for our next interaction with matter.
Hi there, thank you for joining us today. For now, we're going to paint ourselves in a little example of photoelectric effect. So right now we got our canvas set up with a nice little atom right there, but we're going to make a little changes here and there, add a little magic, right? So for a photoelectric effect, you got an X-ray coming in, interacting with the inner shell electron. So we're going to go ahead and add some of those right now. So in the inner shell, you got yourself a little electron here, but you got to put yourself, they got to have a little friend right there. So we're going to put another one right here. Okay, all right, that looks good. Okay, so we're gonna take ourselves a little bit of crimson right here. And so what we're gonna have is we're gonna have a photon coming in, and it's gonna interact with that inner shell electron. It's gonna be completely absorbed. Now, sometimes scatter can happen with the characteristic effect afterwards, but we're not gonna worry about that right now. Right now we're just gonna do the photoelectric effect. So what we're gonna have right here, we're gonna have our photon right here coming on in, coming on in, coming on in, and boom! It's gonna hit our little inner shell electron right there. So what's gonna happen is it's gonna take that electron and then it's gonna kick it out and it's gonna eject it this way right there. Look at that. Look at that. So that will now become what we call a photoelectron. So it's gonna be right over here. Yeah. All right. So I'm gonna go ahead and label this photoelectron right here. There we go. Almost forgot how to spell photoelectron. That would be silly, huh? Well, all right. So now I'm gonna go ahead and explain it a little bit better. So with a photoelectric effect, like I said, you got the X-ray coming in and it's going to interact with that inner shell electron, kick it out and make that photoelectron. Alright, so there's a bunch of different things that can go with photoelectric effects. So as the patient's tissue size increases, it's more likely that that X-ray is going to get absorbed completely. And so that would be increase in photoelectric effect as the tissue size goes up. Another thing is you got these little electrons right here that are trying to hold on, trying to stay right in there, and that's called your binding energy. But if your X-ray energy, it has to be just slightly above that binding energy of that electron to kick it out and make that beautiful photoelectron we got over there, right? Okay. So, and as X-ray energy increases, it's more likely that X-ray is going to penetrate completely instead of getting absorbed. So as X-ray energy increases, you're going to have a little bit less of the photoelectric effect, especially compared with Compton scattering. All right, so now we're going to talk about how the photoelectric effect relates to what you're seeing on an X-ray image. So if we took an X-ray image and we had no photoelectric effect going on, we would just see complete darkness, right? Let's shade that in a little bit right there. That's good enough right there. Now, on the other hand, if we had complete photoelectric effect, like if you had a lot of bone, dense bone, then it would be completely white right there. And so that leads to really high contrast. So if you've got good amount of photoelectric effect going on, you got a higher contrast going on. Now, as the X-ray energy increases, less photoelectric effect, more penetration, then you're gonna go in a more grayer look, more dull look. We don't like that, it's a little sad around here. So, but it depends what you're looking at. If you're looking at an abdomen or something like that, you know, maybe a few shades of gray is pretty good. But if you're looking at bone, you want a lot of that photoelectric to happen. So you go a little bit down on your KVP or something like that. You know, that sounds good. I like that. All right, and so always remember, the photoelectric effect is one of the most important interactions when it comes to X-ray imaging, or paintings we'll call them. We like that sort of thing around here. So join me next time where maybe we'll tackle another painting of maybe another little interaction. Bye-bye now.
Welcome. I'm certainly glad you can join me today. Today I thought that we could do a fantastic little painting that I think you'll really enjoy. So we're going to start off with our Midnight Black here. We're going to call this painting Pair Production. How about that? Very nice. Now, we're just going to draw some circles right about here. Right in the center. Just like that. Just like that. Perfect. So we got about 4 circles right here. We're going to close up this Midnight Black. And we're going to take out our Phthalo Blue. Nice color, don't you think? We're going to draw some little circles right in here. This is what we call our nucleus, right here, right in the center. Next, we're going to draw some little friends right around here. Right there. Look at that. Beautiful. All right. Now we're going to take our forest green and we're going to draw a little squiggly line right about here. Just like that. Yeah. So with pair production, our incident X-ray, right about here. I spelled incident wrong, but you know what? That's all right, because we don't make mistakes. Just happy little accidents. So this is going to be our incident X-rays. Right there. So when our incident X-ray right here has sufficient energy, it may escape interaction with electrons. Because for some reason, this little guy, he doesn't want any friends. So once he escapes his interactions of these electrons, it's going to be influenced by the strong nuclear field right there. The interaction between the X-ray and the nuclear field causes the X-ray to disappear, and in its place, 2 electrons appear. So we'll take out, I guess we'll use our crimson red right here. We'll draw a little line coming out right here. And we'll draw another little line coming out right there. This one's going to be an electron. And this one down here, he's a positive. So we're going to call him positron. Now, like I said, there's 2. Because everybody wants a friend, except for this guy right here. And we're going to draw him right next to him. We're going to call this little guy Negatron. How about that? I like that name. So in this place, 2 electrons appear, 1 positively charged and 1 negatively charged. The energy equivalence of the mass of an electron is to be 0.51 MeV. So we'll draw a little line right here. It's going to be 0.51 MeV. Now since there's 2 and they're a pair, well, this one can't be left out, can it? So this one's also going to be 0.51 MeV.
which is going to equal out to 1.02 MeV. How about that? Beautiful. The most fun part of this whole painting technique is washing the brush, so let's wash the brush. We do that with odorless paint thinner, and I have a screen in the bottom of this can so we can scrub the bristles against the screen, and the solid material sort of settles to the bottom, keeping the paint under relatively clean. I will shake it off and then just just beat the devil out of it. Less than 1.02 can't undergo pair production. The electron that results from pair production loses energy through excitation and ionization, and eventually fills a vacancy in an orbital shell, just like we got right here. How about that? The positron, this little guy down here, unites with the free electron, and the mass of both is converted to energy in a process called annihilation radiation. The most important thing to know about pair production right here is it does not occur in X-ray imaging. Us X-ray students, we ain't got to worry too much about that, huh? How about that? Alrighty, well, I guess this pretty much sums it for this beautiful painting right here. And until next time, I'll show you a new little interaction. How about that? Bye-bye. Welcome back. I'm Bob Ross, and I'm very glad that you joined us today. Today, like I said, we'll be doing a little different interaction today. We're going to call this one a photodisintegration right there. So we're going to start off with our midnight black again. We're going to draw some circles. We've got one here, one there, another one, and we'll just add one more. How about that? Next, to complete our nucleus, we'll get our phthalo blue, and we'll add some little circles right up in here. How about that? Just like that. Make it real magical. Now with photodisintegration, X-rays with energy above 10 MeV escape interaction with the electrons and the nuclear field and is absorbed directly by the nucleus. So we got our incident X-ray right here. Just gonna come across and just label it incident X-ray, just like that. So once it's absorbed by the nucleus is raised to an excited state and instantly emits a nuclear fragment. So we'll go ahead and draw it out. Forest green right here. Just straight out that way. We'll call this the nuclear fragment. Just like that. The most important thing to know about photodisintegration is that it does not occur in diagnostic image. So you ain't got to worry about that just yet. Well, this about sums up this painting. It's a quite simple one for our little beginners. But until next time, friends, thank you.
All right now, so when you're
I am nervous.
she's
I don't like
lashing
this.
out.
Okay,
being
ready?
angry.
Hello. Don't mind me. I was beating the devil.
All right, now.
I need some water.
Do it a straight.
Or paintings, we'll call them. We like that around here. So, just
Hi, I'm Bob Ross, and welcome to the 5-inch Arctillus Matter. Let's get started. Nope, I like it.
Normally, most of the energy is retained to the scattered X-ray. Bob Ross here, how may I help you?
Ooh, a good blue.
So you already.
X-ray less than 1.0. Sorry, I look real stupid.
You're doing great.
I know. Ready?
X-ray image or painting. You always want to take into consideration the photo X-ray, but I feel like I'm talking in circles.
It is the same. It doesn't look the same, but that's okay. We're not all great artists. And this right here was just a happy little mistake. But you get the point. Anyways.
No,
No,
cut it.
this- Compton scattered X-rays can be deflected in any direction, including 180 degrees